All right, so let's start out reviewing some basic exponent rules. So the first rule we can talk about is, for example, say we have x to the fifth times x to the third. And most of you guys know that we can add these exponents. We have the same base of x multiplied together. We add the exponents, you get x to the 8th. But why is that true? So let's think about, what does x to the fifth actually mean? So x to the fifth means to multiply x by itself 5 times. 1, 2, 3, 4, 5. So x times x times x times x times x 5 times. Times, so I have another times, x to the third. X to the third means to multiply x by itself 3 times. So obviously then, you're multiplying x by itself 8 times. So that would be x to the 8th. So you can see pretty clearly why you would need to add these exponents. Okay, so the first rule, if we have x to the m times x to the n, that will be x to the m plus n. All right, what about division? So we have the same base of x, x to the m divided by x to the n. So let's look at an example. Say we have x to the fifth divided by x squared. So again, most of you already know that we subtract these exponents, but why do you subtract these exponents? So let's think about what it means. So x to the fifth means to multiply x by itself 5 times. X squared means to multiply by itself twice. So we get that. Right. And then these x's will cancel, because anything divided by itself is 1. X divided by x is just 1, so those cancel away. These guys cancel away. And you're left with 3 x's multiplied together on the top. So you would get x to the third power. So you can see why you subtract. However many x's you're multiplying down here will cancel with that many up here and leave you with that number minus that number x's multiplied together on the top. So it's pretty clear why you would subtract those exponents. Okay, so rule number 2, x to the m divided by x to the n is x to the m minus n. And what about this rule? X to the m, all raised to the nth power. So let's look at an example of that. Say we had x squared to the third power. Okay, so again, you probably know that you multiply these exponents together and get x to the 6th. But why do you multiply those exponents together? So let's think about that. So x squared, all raised to the third power. Okay, so if we raise this, what I've got under my hand, to the third power, then that means to multiply it by itself 3 times. So this would be x squared times x squared times x squared. Okay. Then by rule number 1, we should add those exponents. X squared times x squared times x squared. The bases are the same, I'm multiplying together, so I should add the exponents. 2 plus 2 plus 2 would obviously be 6. So I have 3 sets of 2's that I'm adding together, so I would be multiplying 3 times 2 and get x to the 6th. Alternatively, we could actually expand it all out. X squared is x times x. That's x times x. That's x times x. And pretty clearly, we have 3 sets of 2 or 6 x's multiplied together. So we get x to the 6th. All right, so our rule would be x to the m times n. Okay. Multiplication is commutative, so you can multiply in any order. M times n is the same thing as n times m, so it shouldn't matter which order we write these in. We could put the n here and the m here, and we would still get the same answer. So for example, if I did x to the third squared 3 times 2 is still 6, no matter which order you multiply them. So this still should be x to the 6. And obviously, if we work it out, it would be.
Pardon the interruption, just a reminder to teachers, I think we've had some miscommunication.
All right, so if we have x to the third squared, x to the third just means x times x times x. If we square it, we multiply it by itself. So we get that. And pretty obviously, we have 6 x's there, so that would be x to the 6th power. So it doesn't matter which order those two numbers are in. So we can say that that would be equal to x to the n raised to the m power. So we can do this in either order, m times n or n times n. All right, so what about this one? X times y, so different bases, all raised to the m power. All right, so let's look at an example. Say we have x times y to the third power. All right, so if I raise something to the third power, that means to multiply it by itself 3 times. So this would be xy times xy times xy. Multiplication is commutative, so I can multiply in any order. So I can do, so all I'm doing is multiplying all these, x times y times x times y times x times y. So I can multiply all my x's first, so x times x times x, and then I could do y times y times y. And then pretty clearly, you would have x to the third times y to the third. So it's fairly obvious that this exponent should apply to both of those, to the x and to the y. Okay. So if I have x times y to the m, that would be x to the m times y to the m. All right, one mistake that I see often is this. Okay. So instead of x times y squared, which would be x squared times y squared, we have x plus y squared. Don't make this mistake. This is not equal to x squared plus y squared. Okay. This 2 cannot just apply to both of those. Obviously, as we've done many times, x plus y squared would be this, x plus y times x plus y multiplied by itself. And then you'd have to distribute it, and you would get x squared plus xy plus another xy. That would be 2xy plus y squared. Okay, so if this is a plus or a minus in here, x plus y squared, you get this. You have this middle term. It's not just equal to that. You cannot just apply the exponent to both of those terms. So don't make that common mistake. All right, so what about x over y to the m power? So for example, say we had x over y to the 4th power. Okay, if I raise something to the 4th power, then I multiply it by itself 4 times. So I would have x over y times x over y times x over y times x over y. Okay, so I multiplied all these fractions together, so I just multiply the numerators. So x times x times x times x, that's x to the 4th. And y times y times y times y, that's y to the 4th. Okay, so again, this 4 applies to both the x and the y. So x over y to the m would be x to the m over y to the m. All right, so far we've talked about rules where we raise numbers to natural numbers like 1, 2, 3, 4, 5, 6, and so forth. But what if we included 0 in that? What if we wanted to raise a number to the 0 power? So what does that mean? What would the answer to that be? Maybe you think the answer should be 0. If I multiply something by itself 0 times, then the answer should be 0. But let's see if we can figure out what it needs to be. All right, so suppose, for example, that I had x to the third over x to the third. All right. So the numerator and the denominator are equal to each other. So if I divide something by itself, what do I always get? What's my answer? Well, 7 divided by 7 is 1. 10 divided by 10 is 1. Anything divided by itself, other than 0, you can't have a 0 on the bottom, but anything divided by itself is always equal to 1. Because anything divided by itself is 1. Because anything other than 0, of course, 0 cannot be on the bottom of the fraction. All right, but let's think about this a different way. So, but x to the third divided by x to the third should also be equal to what if we use rule number 2? Rule number 2 says I should subtract those exponents. So this should be equal to x to the third, or x to the 3 minus 3, by rule number 2. 3 minus 3 is 0, so I get x to the 0 power. Okay, so we know x to the third divided by x to the third has to be 1. I mean, that's just basic arithmetic. Anything divided by itself is 1. But if we want rule number 2 to keep working, even if these exponents are the same, then this also has to be x to the 0. Okay, so x to the third divided by x to the third is 1, but it's also equal to x to the 0 by rule number 2. That means that x to the 0 has to be 1. Okay? And it wouldn't have mattered what these numbers were, whether this was a 3 or it could have been a 7, x to the 7 divided by x to the 7. It would still be 7 minus 7. Your argument would always be the same. Okay, so we need to define, as long as we want rule number 2 to keep working, we need to define x to the 0 to be 1. As long as x is not 0. So remember, we don't want a 0 on the bottom of our fraction, so x is not 0. So anything other than 0 to the 0 power is going to be 1. All right, so far we know how to raise numbers to whole numbers. 1, 2, 3, 4, 5, 6, 7, and so on, along with 0 now. But what if we wanted to raise exponents to all integers? What if we wanted to include the negative natural numbers, like -1, -2, -3, -4? So what would it mean to raise a number to a negative power? Okay, so let's look at an example. What about x to the third divided by x to the fifth? Well, let's think about what this means. So this means to multiply x by itself 3 times. This means to multiply x by itself 5 times. So these x's will cancel, as long as x is not 0. These x's will cancel. These x's will cancel. Make sure you understand there's an understood, you can multiply by 1 up here and it wouldn't change anything. Right? So times 1, nothing changes. So after all those canceled, I'm left with 1 over x squared. So I have 3 x's multiplied together on the top, 5 x's multiplied together on the bottom. These 3 x's would cancel with 3 x's down here and leave me with 5 minus 3 x's on the bottom. So I get 1 over x squared. All right. But what does rule number 2 say that we should do to those exponents? Well, rule number 2 says base is the same. I should subtract the exponents. So this should be x to the 3 minus 5. Well, 3 minus 5 is -2. So here we have a negative exponent. And if this, x to the third divided by x to the fifth, is equal to x to the negative 2 by rule number 2, and this is also equal to 1 over x squared, then 1 over x squared should be equal to x to the negative second. And that would work no matter what these exponents were. If your exponent on the bottom was bigger than the exponent on the top, you would always come out with a negative exponent by using rule number 2. And you would also come out with more x's in the denominator down here. So that's what the rule is always going to be. If you have a negative exponent, we will sort of flip this upside down and you have 1 over x squared. All right, so x to the negative m power will be 1 over x to the m power. All right, so before we talk about our next rule, let's do a little review here. So 1 to the third power is 1. 2 to the third power, 2 times 2 times 2 would be 8. 3 to the third power, 3 times 3 times 3 would be 27. 4 to the third power, 4 times 4 times 4. Well, 4 times 4 is 16. And then 16 times 4. 16 times 2 is 32, so that would be 64. 4 times 6 is 24, carry a 2, 64. So 4 to the third is 64. 5 to the third, 5 times 5 times 5. 5 times 5 is 25. 25 times another 5 is 125. So you need to be pretty familiar with those numbers. We'll use those a lot. So the inverse process of this would be the cube root. Okay, so the cube root of 8. Okay, so we say that the cube root or the third root of 8. Okay, so what this means is what number do you raise to the third power to get 8? Well, obviously that's 2. So the cube root of 8 is 2 because 2 to the third is 8.
Rachel Harris, call 1-200, please.
What's the cube root of 27? Okay, so what number do we raise to the third power to get 27? Obviously that's 3. What's the cube root of 125? Okay, so what number do you raise to the third power to get 125? Obviously that's 5. All right, let's do some others here. Some other numbers you should be familiar with. So 2 to the first power would be 2. 2 squared would be 4. 2 to the third, we've already mentioned, that's 8. Okay, what about 2 to the fourth? Well, that's 16. 2 to the fifth, that would be 16 times 2, so that would be 32. 2 to the sixth, 32 times 2 would be 64. 2 to the seventh, that would be 128. So you need to be very familiar with these numbers, 2, 4, 8, 16, 32, 64, 128. Okay, because we're going to ask questions such as, what is the fifth root of 32? Okay, so what number do you multiply to the fifth power to get 32? And that would be 2. Or what number do you raise to the seventh power to get 128? So the seventh root of 128 would be 2. All right, let's look at some interesting examples here. So what's the square root of 25? Well, that means what number do you square or multiply by itself to get 25? Obviously, that's 5. What about the negative square root of 25? So the square root of 25 is 5, so it would be negative 5. And what about the square root of negative 25? So what number do you square to get negative 25? Well, there's no real number that you can multiply by itself and get negative 25, but there is an imaginary number. We talked about this several lessons ago, and you guys know that that's 5i. Okay. So just to double check that, if I multiply 5i by itself, so 5i times 5i, I get 25i squared. And as you remember, I squared is equal to negative 1. So 25 times negative 1 is negative 25. So 5i would be the square root of negative 25. All right. What about the fourth root of 16? So what number can we multiply by itself 4 times and get 16? Now that would be 2. 2 times 2 times 2 times 2 is 16. All right. Negative fourth root of 16, that would be negative 2. All right. What about the fourth root of negative 16? So there's no real number you can multiply by itself 5 times or 4 times to get negative 16. So for example, if I thought the answer was negative 2, let's say, if I did that 4 times, I multiply that by itself 4 times, negative 2 times negative 2 times negative 2 times negative 2. Well, this would be positive 4. These two multiplied together would be positive 4, and I would get a positive 16. So if I raise a negative number to an even exponent, I'm going to get a positive answer. But I'm supposed to get negative. So there's no real number that's going to work. Okay, so that's not real. The answer can't be a real number. All right, so maybe you think it's just like up here. Maybe this is 2i. Okay, that seems to make sense. It's an imaginary number, so maybe it's 2i. Let's check that and see. So if the fourth root of negative 16 is 2i, then 2i times 2i times 2i times 2i should be equal to negative 16. Let's see what it's equal to. So 2 times 2 times 2 times 2, that's 16. I times I times I times I, that's I to the fourth. What's I to the fourth? So you remember our little circular pattern. So I to the first power was I squared was negative 1, I to the third was negative I to the fourth was 1. So this would be 16 times 1, which is also 16. So the answer can't be 2i, so that's not right. Okay, I'll leave it to you guys to see if you can figure out what the real answer actually is. But for right now, we will just say that this is not real. So it's not a real number. We don't really know what it is. Maybe you can figure it out. But we'll just say that it's not real. All right. What about the cube root of 8? So what number do I raise to the third power to get 8? Well, that's 2. Negative cube root of 8. If the cube root of 8 is 2, then this answer would be negative 2. What about the cube root of negative 8? So what number can I multiply by itself 3 times to get negative 8? Well, that would be negative 2. Because in this case, I have 3 negative signs multiplied together. So if I multiply the first 2, that would be a positive 4. Times a negative 2, that would get me a negative 8. So I have an odd exponent. Multiplying this number by itself an odd number of times, that will give me a negative number. So if I have the odd root of a negative number, my answer can be real. Okay, for example, the fifth root of negative 32 would be negative 2, because negative 2 to the fifth, that's an odd exponent. So if I did negative 2 to the fifth, I would get negative 32. That works. However, the sixth root of negative 64 is not negative 2. That's not real, because this time I have an even exponent. All right, so let's look at some more interesting and useful facts. Okay, so what's the square root of 9 squared. Okay, so if we worked it all out, the square root of 9 would be 3. And 3 squared would equal 9. So notice those are inverse processes, right? If I take the square root of 9 and then I square it, I get right back to where I started because square root and squared are inverse processes. Okay, so what would be the square root of 7 squared? Well, that would be 7. What would be the square root of any positive number squared? That would be x. What about the cube root of 8 cubed? Well, the cube root of 8 is 2. And then 2 to the third is 8. Okay, so again, those are just inverse processes. Cube root and cube are just inverse. They undo each other. Okay, so if I do the cube root of 8, I'm finding the number that I cubed to get 8. So when I find that number, if I cube it, I get the number back that I started with. Okay, so what's the cube root of any positive number cubed? Well, that would just be that number. All right. The 7th root of 128, well, the 7th root of 128 is 2. And then 2 to the 7th is 128. I get exactly back where I started. So the 7th root of x to the 7th would be x. All right, so some more useful examples here. So what's the square root of 5 squared? Well, 5 squared is 25. And the square root of 25 would be 5. So again, those are inverse processes, square root and square. If I square a number and then take a square root of it, I get right back where I started. So 125 to the third cubed. Well, 125 to the third is a really big number. I don't know what it is in my head. But if I cube that number and then I take the cube root of it, I get back where I started. I would get 125. 5 to the 7th power. So this one is true. I actually meant to use a little better example here. I meant to do this, so let me change that for you. Let's do this instead. A cube root of 5 to the third. Obviously, you know the answer should be 5, but let's work it all out. 5 to the third is 125, and the cube root of 125 is 5. So I get back where I started because raising something to the third and taking the cube root are inverse processes. Okay, now let's try this one. The 7th root of 5 to the 7th. Now, I have no idea what 5 to the 7th power is, but I do know that if I raise 5 to the 7th, and then I take the 7th root of that huge number, I would get 5. I don't know why I made all those examples be 5. I could use some different numbers for variety. But anyway, so what's the 9th root of x to the 9th power? Okay, well, that would be just x. I would get back to where I started. If I took a number, raised it to the 9th power, and then took the 9th root, I would get x. All right. What about the nth root of x to the nth power? So if I took any number, raised it to the nth power, and then took the nth root, I would get x out of it because the nth root and the nth power are just inverse processes. All right. Then going the other way, what if I did the square root of 7 and then I squared it? I have no idea what the square root of 7 is. I know approximately what it is, but I couldn't say it because it's an irrational number. But whatever that number is, when I do the square root of 7, if I squared that number, I would get 7 because those are inverse processes. All right, the 5th root of 13, no idea what that is. But if I raise that number to the 5th power, I would get back where I started because that's the definition of what the 5th root and the 5th power mean. All right, so what's the 12th root of x to the 12th? Well, that would be x. What's the nth root of x to the n? Well, that would be x. So if I took the nth root of any number and then raised it to the nth power, I would just get back to where I started. Okay, so notice these two last ones are both equal to x. Both have the nth root, but notice that the n here is on the outside and here it's on the inside. And it seems to have made no difference to the answer. All right, so is this really a true statement? So we had this down here at the bottom and it looked really true based on our examples. Is this really true? All right, so let's pretend that x is equal to -5. Okay, so let's say x is -5. Okay, so here, and let's say that our n is 2. Okay, so we're going to, n is going to be 2, x is going to be -5. So here I would have the square root. You could put a 2 there, but the 2 is understood. So when n is 2, it's just square root of -5 squared. Okay, remember we're going to say that x is equal to -5 and n is equal to 2. Right, so x should be -5. All right, the square root of -5, well, that's square root of 5i squared. All right, square root of -5 is square root of 5i. Okay, if I square that, square root of 5i times the square root of 5i, well, the 2 applies to both of these, right? So square root of 5 squared would be 5i squared. I squared is -1, and I get -5. Okay, that's what it should be. So x is -5, that's what we said it was. All right, so everything's good. We got exactly what we expected. Okay, let's look over here. Okay, so if I put a -5 in for x and a 2 for my n, that should be the square root of -5 squared. All right, what is -5 squared? Well, that's 25. Okay, the square root of 25 is, square root of 25 is 5. And that's not equal to -5. That's bad. All right, so this is not completely true, this statement. This is only true if your x is a positive number. Okay, so I should always say that, but I'm not going to. So in all the examples that we do, we're always going to assume that the x is a positive number so that we don't get anything messed up. Okay, so just always assume x is a positive number when it needs to be. And we'll go with that so that we don't run into this issue. All right, so far we have rules for raising numbers to any rational number, any fraction, or any positive fraction. Now, we can raise it to, let me try that again, we can raise it to any integer so far. So 0, 1, 2, 3, 4, 5, -1, -2, -3, -4, -5, and so on. But what about fractions? How do we raise a number to a fractional exponent? We want to be able to raise numbers to any rational exponent, so that means we need to include some fractions. All right, so let's start off with this one. 9 to the 1/2, what does that mean? What would be the answer to that? So maybe you think that means I multiply 9 by itself half of a time. So if I multiply 9 by itself half a time, that sounds kind of like maybe I just take half of 9. Maybe the answer is 4.5. So that would be a good guess. But we don't know for sure what we want it to be, so let's say that we don't know. Maybe it doesn't make any sense. It's just a question mark. Okay, just for fun, what if I raised both sides of this equation to the second power? Okay, what does rule number 3 here say that I should do to these exponents? Well, I should multiply them. What is 2 times 1/2? 2 times 1/2 is 1. So I would have 9 to the first power is equal to question mark squared. 9 to the first is just 9. So I have 9 is equal to question mark squared. So what could question mark be? Question mark would be 3. Right? 3 squared is 9. So the answer should be 3. Well, what's the relationship between 9 and 3? Well, 3 is the square root of 9. So maybe 9 to the 1/2 means the square root of 9. Okay, let's try another example. Let's do 8 to the 1/3 power. What is that? What's the answer to that? What does that mean? Does that mean we divide 8 by 3? Who knows? Let's just say it's question mark. What if I raise both sides of this, just for fun, to the 3rd power? If two things are equal, I can do the same thing to both of them, and they should still be equal. Rule number 3 says that I multiply these exponents. 1/3 times 3, or 1/3 of 3 is 1. So I get 8 to the 1st, or 8. So 8 is equal to question mark to the 3rd power. So what number do I raise to the 3rd to get 8? Well, that would be 2. So the answer to 8 to the 1/3 should be 2. That's unreadable. So what's the relationship between a 2 and an 8? Well, 2 is the cube root of 8. So maybe 8 to the 1/3 means the cube root of 8. All right, so let's see if we can prove our conjecture about what we think this is. So just as in the previous example, if we had x to the 1/3, we kind of thought that that meant the cube root of x. So we might guess that x to the 1 over n is the nth root of x. All right, so, but let's pretend we don't have any idea. So let's just say that that's equal to question mark. And so I'm going to raise, just for fun, both sides of this equation to the nth power. Okay. By rule number 3 over there, I should multiply these exponents. So 1 over n times n is n over n, or just 1. I'm going to write this out really carefully. So x to the 1 over n times n is x to the n over n. Equals question mark to the n. N over n is 1. So I have x to the 1st power is equal to question mark to the nth power. Well, x to the 1st is just x. So I have x is equal to question mark to the nth power. Let's take the nth root of both sides of that equation. Okay, so I have x equals question mark to the n. And I'm going to do the nth root of this side. And I'm going to do the nth root of that side. So what is the nth root of question mark to the n? Well, that's obviously just question mark. So question mark is equal to the nth root of x. But what was question mark? Question mark was x to the 1 over n. So that means that x to the 1 over n has to equal the nth root of x. And notice that we made the assumption here that x had to be bigger than 0 so that we avoid that little issue we had a few minutes ago. So as long as x is bigger than 0, x to the 1 over n has to equal the nth root of x. All right, so we have x to the 1 over n is equal to the nth root of x. Just for fun, let us raise both sides of this equation to the m power. Okay, so I'm going to raise that side to the m, and I'm going to raise this side to the m. Well, 1 over n times m is m over n. So I have x to the m over n equals the nth root of x to the m power. So now, whereas before we could raise any positive number to the 1 over n power, now with rule number 9, the numerator doesn't have to be a 1, it can be any number now. So the x to the m over n is the nth root of x to the m power. All right, so one last rule to note here. So I have x to the 1 over n raised to the m. That's equal to nth root of x to the n. That's how we proved the last one. Okay, and of course, 1 over n times n is x to the m over n, which is our rule here. But notice that I can switch these two around, as we talked about in rule number 3 over there on the board. So this is also equal to x to the m raised to the 1 over n. In this case, then, I would have x to the m. So this one thing, and I would take the nth root of that. But now both of these are equal to, both of them all together is equal to the x to the m over n. Because 1 over n times m is m over n, and m times 1 over n is m over n. So that means that x to the m over n power is equal to either one of these. So both of these are the nth root, but notice that here the m is on the inside of the radical. Here the m is on the outside of the radical. So as long as x is a positive number, it should make no difference whether your m is on the inside or on the outside. So let's add that to our rule. So x to the m over n is equal to the nth root of x to the m, or it's also equal to the nth root of x to the m, with the m on the inside of the radical. And just for more room on our board, I'm going to write that underneath here. So that's the nth root of x to the m on the inside of the radical. So sometimes it's useful to write it like this, sometimes it's useful to write it like that, but they are the same thing as long as x is a positive number. All right, I lied to you. I want to do one more rule, even though it's not really a new rule, but kind of an application of a couple other rules. So say that we have x over y to the negative m power. All right. So what does it mean to raise something to a negative exponent? So rule number 7 says that that means 1 over that. Okay, so consider this all one thing under my hand. So I have my hand raised to the negative m power. So that would be 1 over my hand raised to the m power by rule number 7. Right. So that's 1 over. Now rule number 5 over on the board says that if I have a fraction raised to an exponent, that exponent can apply to both of those. So that would be 1 over x to the m over y to the m. Like that. Right. I have 1 over a fraction. So dividing by a fraction is the same thing as multiplying by the reciprocal. So that would be 1 times y to the m over x to the m. Well, 1 times anything is just itself, so that's y to the m over x to the m. But now if I do rule number 5 backwards, so we can get rid of this 1 now. So if I do rule number 5 backwards, I can rewrite y to the m over x to the m as just y to the x, or y over x to the m power. Okay, so notice what happened. So I had a fraction raised to a negative exponent. This negative exponent caused the fraction to flip upside down. So it was x over y, now it's y over x. And the exponent became positive. Okay, so our rule is x over y to the negative m is equal to y over x to the m power. And that's a useful rule to use sometime. Even though it's not really a new rule, it's just like rule number 5 and 7 combined. All right, let's do 11 example problems here. So why don't you try these on your own first? So pause the video, see if you can work these out, and then we'll go over the solutions. All right, so number 1, we have 5 to the negative second power. All right, so number one, we have 5 to the negative second power. So which rule applies there? Well, that's rule number 7. 5 to the negative second will be 1 over 5 squared. So that's 1 over 5 squared. That would be 1 over 25. All right, 2/5 to the negative third. Okay, so rule number 10 tells us what to do with a fraction raised to a negative exponent. I can flip the fraction, make that 5 over 2 to the third. All right, and then rule number 5 tells us how to handle this. This 3 can apply to both of those, so it would be 5 to the third, 2 to the third. 5 to the third is 125. 2 to the third is 8. All right, 1/2 to the negative seventh. Okay, so again, rule number 10 tells us how to handle a fraction raised to a negative exponent. I just flip it. So 1/2 flipped upside down is 2 to the 7th, and 2 to the 7th is 128. 16 to the 1/2 power. Well, that's rule number 8. 16 to the 1 over 2 would be the second root of 16. So that would be the square root of 16. Okay. And again, if it's a second root, that's understood to just be the square root. Square root of 16 is 4. So 16 to the 1/2 is 4. All right. Negative 16 to the 1/2 power. So that would be the square root of negative 16. And you guys know that that is 4i. All right, 125 to the 1/3 power. Well, that means the cube root of 125. Cube root of 125 is 5. All right, negative 8 to the 1/3 power. So that means the cube root of negative 8. Okay, 3 is an odd root, so this will be a real answer. This will just be negative 2. And I'm going to make myself some more room. All right, so 32 to the negative 1/5. Okay, so we have a negative exponent. So that would be the same thing as 1 over 32 to the 1/5 power. Okay, and then this 1/5 would apply to both those, so I would have 1 to the 1/5. 1 to any power is just 1. So that would be 1 over 32 to the 1/5. 32 to the 1/5 is the 5th root of 32. So 1 over 5th root of 32. 5th root of 32 is just 2, so I get 1/2. All right, let me try to explain number 8 a little differently, maybe a little better. So I have 32 to the negative 1/5 power. So according to rule number 7, I should flip that upside down. So that would be 1 over 32 to the 1/5. So a direct use of rule number 7. 32 to the negative 1/5 would be 1 over 32 to the 1/5. All right, and then 32 to the 1/5 means the 5th root, 32. And the 5th root of 32 is just 2. So I get 1/2. All right, let's try number 9. So I have a fraction raised to a negative number. Rule number 10 says to just flip the fraction. So that'll be 9 over 25 to the 1/2 power. So rule number 10. All right, rule number 5 says that that exponent applies to both the 9 and the 25. Raising something to the 1/2 is same as taking the square root. So this will be the square root of 9 over the square root of 25. So we get 3 over 5. Or alternatively, you could have just said, since all of this fractions in the 1/2, then you could say the square root of 9 over 25, which you can still see is 3 over 5. All right, we have 8 to the 5/3 power. So this is a direct use of rule number 9. So we have 8 to the 5/3 power. So that would be the cube root of 8 to the 5th. Or it could be the cube root of 8 to the 5th with the 5 on the inside. What if we tried to evaluate this? Here we would have to do 8 to the 5th. I have no idea what 8 to the 5th is. I would need a calculator. But this side I can do. The cube root of 8 is 2. So I have 2 to the 5th, which is 32. Okay, so 8 to the 5/3 power would be 32. All right, one last example. All right, so I have a fraction raised to a negative number. So the first thing I'm going to do is apply rule number 10. And I will get 16 to the 3 over 2 power. The reciprocal of 1/16 is just 16 to the 3 over 2. All right, now by rule number 9, 16 to the 3 over 2 will be the second root of 16 to the 3rd. So the square root of 16 to the 3rd. Square root of 16 is 4. 4 to the 3rd is 64.